bang. So it's not supposed to hit the wall. But remember, this is like a baby learning to walk. This is just a very young brain, 2 weeks old, and some of the time it'll get it right and some of the time it won't. There we go. That was good. That's cool. That's not so good. There we go. So what we can witness in the culture, in the brain, as the robot moves around is Hebbian learning. The basic learning, when one neuron fires and stimulates another neuron to fire, it strengthens the connection between the neurons. You can witness this under the microscope as the robot moves around. So every time it gets it right, every time the robot goes to the wall, I mean, that's not so good, but it doesn't really matter here if it gets it wrong. That's not, if it gets it wrong in different ways, is not important. There, so when it got it right, that will strengthen the neural pathway that did that made that choice. So what you're getting is the same thing for humans. Every time you do something and it works all right, it's actually strengthening the neural pathways in your brain, becomes more likely you're going to do that again. So with some things that become habitual, you do it without thinking, well, in a way you are thinking, but the pathways are so direct that you don't realize you're thinking about it. You're doing it without thinking, you feel. But that's what we can see in the robot here. Now I will switch to the robot after 2 months. So this is the same robot we're going to see. All it's been doing, I mean, it's a simple thing. It's taking an ultrasonic sense, a sonar sense, which gives an indication of distance, and it's trying to turn when it comes to the wall. And that was after 2 weeks. We will now see the same robot after 2 months, where that's what it's been doing. And to be honest, I shouldn't sort of introduce a video saying this is boring, but it will be quite boring, as you'll see, because the robot, here we go. So you saw what it was like at an early age. There we go, picks it up quite early on, confident, no problem at all. There we go. I mean, I say it's boring, really. I mean, the row's just picking up the signals. And I think this particular sequence I picked was a very good, you know, this was the top student in the class as far as the brain developed. I think we go through here, as far as I can remember, it doesn't actually hit the wall at all, which is unusual. Usually, it might make a mistake occasionally and hit the wall. It didn't quite get the signal, or it was thinking about something else at the time, or whatever it happens to be. So you get, we would typically have 25 to 30 brains developing at any one time, so they have to time share the body essentially, and then so we can compare the development of the brains, and some of them you get, like this one, yeah, it's very confident, it's swaggering around, yeah, I can turn right here, no problem. And then you get others that can be hesitant and are not sure what they're doing, and oh, is there a wall there? I mean, maybe I'll go left, no, maybe I'll go right, a bit like that. We also give it a bit more to do. Sometimes it can turn right or left, and it has to decide what it's going to do. And some of them you get habitually decide, I'm going to turn right all the time, I know what I'm doing. And some will change, some will start to go backwards a bit. And so you get all sorts of different, some of them can do funny things in corners, from just when you think it's got it sorted out, and it'll start swinging around in a corner, just, you know, maybe a little bit schizophrenic or something like that. But you can see the whole point of looking at what's going on in the brain and trying to relate that to other things. But I mean, I told you, it's boring, isn't it? It's just going around and it's not, but you can watch it like a goldfish in a bowl, I guess. Observations. Hebbian learning, clearly we can observe. Other reinforcement learning with chemicals, yes, we can go in and enhance growth in areas or restrict growth. So we can reward and punish chemically. Electrically, don't know, you know, if we could find a way of applying electrical or electrochemical stimulation, then of course we'd be doing it to all our students. So you will learn this and so on. So if we can do that, it will have widespread appeal, I'm sure. Sleep time. Of course, a lot of the time the culture is in the incubator. It has to be kept at 37 degrees centigrade, and but it's still active. The brain is still sending what appear to be representative signals within it, even when it's not connected to its body, which gets very, very Kafka-ish. Well, what is it thinking about when it's not in its body? Typically, 100,000 brain cells are involved for the rat culture. We don't count them individually, of course. I mean, that's it's sort of the sort of thing they do up at Oxford, where they haven't got anything else to do. But our students try and do some research. So, I mean, it could be maybe up to 150,000 is about the tops. But it varies. It's very rough 100,000. But that's a typical figure. Of course, that in comparison, the human brain, 100 billion is the typical figure. Because if there are any Americans here, we're told it's 200 billion for Americans, but for the rest of us it's 100. Just to get me shot. 100 billion is a typical figure. I'm just quoting. Just quoting. If you read Time magazine, then it's anyway. There we go. This is interesting. Neuron speciality. I mean, as we'll see, some philosophical complaints could be yes, but in the human brain, the neurons specialize. We have some which deal more with sensory signals, some which you actually get this. You get with the brain the neurons that are around the electrodes we use for stimulation become unidirectional. They only really operate in a sensory sense. Others motor. Some of them in sending signals from place to place, and then, quite amazingly, there seem to be some neurons that sort of sit back and start to tell the other neurons what to do, which is interesting. So, I mean, this is very much, this is what we observe. Actually publishing that at this stage would be very difficult, but there appears to be a brain within a brain. The brain is doing the controlling of what the lower neurons, can I call them lower neurons? I'm not sure, but the sensory and motor neurons that are just doing their job, they're sort of pretty boring. Then there are other neurons telling them what to do. Old age, at the moment, Steve Potter from Georgia Tech says he can keep them alive for about 2 years. But we find after about 3 months that they're really suffering from old age. They stop really functioning. You have to increase the volume of the signals, and it's still, I'm not sure what I'm doing. It really is like an old person. It doesn't listen to what you're telling it, and it knows what it's doing. And old academic, I'm just going to do it this way. Now on to the philosophy, which I think is great, because this, as you know, if you're into philosophy of artificial intelligence, it's a big area. A lot of people have made big reputations. Daniel Dennett, John Searle, Roger Penrose made big reputations, which this really stirs up things quite a bit, as we'll see, as far as they're concerned. The problem being that the philosophy of AI till now has been based on a comparison, humans and computers. Silicon in terms of the computers, the humans, the carbon form, and so on. So there's different technology that's involved, and you can draw conclusions based on those differences. So can we pull some little nuggets, some important points from classical artificial intelligence and turn them on their head a little bit? Because in the future, we need more robots around the home. Everybody says that. The Western world, more older people can't look after themselves. We need robots to look after them. Maybe we will have robots not with rat neurons, but with human neurons. Now I say that in bold letters there because we have human neurons which we're working with. We actually buy them. I say human. We buy them from an American company. So they're American. No more American jokes. That's close to humans as we can get, but they're American. So we have human neurons which we're working with and so on. So this is quite possible to have human neurons. They don't have to be rat neurons. All sorts of ethical questions with that, but so on. They're actually, the human neurons we have are from abortions. No, we don't do the abortions, we just buy them from the company. But it could be, of course, you know, maybe the human neurons in your robot around the home could come from a loved one. Or you know, maybe if they're going to die, you say, well, let's have some of your brain cells and put them in. Or it could be yourself. I know a lot of important academics want to live on. Well, this is an opportunity. Just take some of your neurons just before you die and live on around your university. The university here could have, Andre, maybe in the future, a robot version of yourself wandering the corridors for years to come. Of course, it doesn't have to be in a little wheeled robot. It can be a walking robot or humanoid. And it raises questions, you know, emotions. This now, if we're looking at human neurons in a robot body, does it have emotions? I mean, you'd like to think if it was your brain, it doesn't matter, what's the importance of your body? If your brain is now in a robot body, does that stop it being emotional? Does it stop it loving or feeling or being angry? Well, I don't think so. So isn't this robot emotional? Is it conscious? Because this is nice, because it opens up all sorts of philosophical arguments. Ongoing, where's the research heading? Well, more senses, clearly. The ultrasonics are limiting. I have a student putting audio input in so that we can start communicating with the robot, but we're getting audio output instead of just moving around, that it can communicate with us. Another student's putting a camera on so to give it some rudimentary vision, but you know, give whatever senses you want to give to the brain. Motor skills as well, if it's walking or picking up things. It's an open book as to what you want to do. The use of human neurons, I'll be critical there, is very, very important. If we're relating it to human mental problems, then it's better if we use human neurons rather than rat neurons. Operating, I think it's called 24/8, but 24 hours a day, 7 days a week, 365, rather than just for an hour a day. Immersing it in the body from straight away. Looking at the environment changes and how that affects the development of the culture. This is one of the important points, working with a group from Canada to culture in 3 dimensions using a lattice structure. The pharmacy guy I works with, he doesn't like this because with 3D we don't know what the neurons in the center of the brain are doing. With 2 dimensions you can see everything that's going on. With 3D you lose contact with the neurons in the middle unless you start putting electrodes in, which is what we don't want to do. But from a systems point of view, it's great because instead of 100,000, this is just putting 3 dimensions on the 2 dimensions. So instead of 100,000, we have 30 million, which is, this is quite good. You're getting into the same sort of brain power